now that we have a good handle on how much radiation we receive at the top of the atmosphere, we're going to start to look at what happens when that radiation enters into the Earth's atmosphere. So we're going to look at the disposition of monochromatic radiation. By monochromatic, we're talking about a single wavelength. And then you can expand that to multiple wavelengths. So we have an incoming irradiance from the top of the atmosphere. That could be S if you want to think of it that way. And we have an atmosphere, which I'm essentially saying is a one-layer atmosphere. It has an absorption component. Some of that incoming radiation is going to be absorbed. Some of it's going to be transmitted down to the surface, and some of it's going to be reflected off of that surface. Where we have our definitions of A is equal to our absorptivity, and A, by definition, has to be between 0 and 1. R is the reflectivity, which must be between 0 and 1. And tau is the transmissivity, which also must be between 0 and 1. So conservation of energy dictates that the total amount of radiation that we have, that radiation that's coming into the Earth's atmosphere can either be absorbed, reflected, or transmitted. But you can't create energy in this system. You only have a certain amount coming in, and you have to do bookkeeping to keep track of where that radiation is going once it enters into the Earth's atmosphere. If you divide both sides by the F of lambda, you'll end up with the following relationship of 1 is equal to the absorptivity at a given wavelength plus the reflectivity at a given wavelength plus the transmissivity at a given wavelength. And this is for a transparent surface. If that surface is opaque and the transmissivity goes to 0, then the only thing that can happen to that incoming radiation is either it can be absorbed or it can be reflected. So clearly the Earth's surface is an opaque object that can either be absorbed or that can either absorb the radiation or reflect it. The Earth's atmosphere is a transparent object that lets some of the radiation through. So we have absorptivity, reflectivity, transmissivity. We've already talked about emissivity, which was the fraction of the radiation that is emitted for an object relative to the black body. And I'm not going to go through the derivation. If you want to, it's in the Wallace and Hobbes textbook. But Kirchhoff's law basically states that the absorptivity of an object at a given wavelength is equal to the emissivity of an object at that same wavelength. And it kind of makes sense. If you have an object that absorbs radiation at a particular wavelength, that means that that wavelength is able to excite some kind of vibrational mode in that object. And if there's a resonance with that particular frequency for the absorption, then that object will still vibrate at that same frequency and will be able to emit that radiation with an equal efficiency. So that's Kirchhoff's law, and so I just wanted to include the emissivity here so that we could show the relationship between the absorptivity and the emissivity.